Hey guys, welcome to first day of rational expressions. This will be about the last unit we do. It may not be the very last one, but it'll be close. We are going to talk just very briefly about the graph, but not very long because we're going to talk about that later. I just want you guys to get like at least a picture. So a rational expression is an expression that is a ratio. That's why we call them rational, like a ratio. And the important thing about the ratio is that there's an x or some expression with x on the bottom of the fraction. That's what makes it a rational expression, or at least an interesting one. And the graphs of these things they always have they usually have branches, and you'll see what I mean when I graph it. We could graph a few points on here, like when x is 1, f of x is you put a 1 in for x, you get 1 over 1 equals 1. So when x is 1, the function value is 1. And when x is 2, the function value is 1/2 by the same logic. And when I'm not going to keep writing all these down, when x is 3, the function value is 1/3, and then it's 1/4, and it keeps getting smaller. But if I go maybe if I say if I take a x equals a 1/2, if I put 1/2 in here for f of x, I get 1 over 1/2, which is really equal to 2. 2 1/2s fit into 1. That's how division works. So we go when x is a half, y is 2. And similarly, when x is a third, y is 3. And when x is a fourth, y is 4. So you get this kind of branched curve. I'm doing a very poor job drawing it, but it's this drawing tablet that's screwing me up. But it basically looks like that. And the other side, that's terrible, particularly up here. But pretty much sketch-wise, it looks like this. It's like a sweeping branch of sorts. And you get another one down here that looks a lot like that. They look like, that looks like a hard turn, but let's make that a little bit better. You get these two smooth branches that look like this. And the branches there's always two of them. And we'll talk a little bit here about continuity. That means this is a mathematical term. That basically means are there any holes? Are there holes in the function? Or they're and kind of one way to think about it, a very non-mathematical way, is can you draw the function without lifting up your pencil? It's kind of an intuitive way to think about it. And if you look at this graph, you clearly cannot. If you tried to draw this thing, you'd have to do this and then pick your pencil up and draw this other branch. So no is the answer to this question. These things are not continuous. They have no continuity. And domain restrictions, the domain restriction is, I think we talked about this earlier in the year. This is, are there values of x which make f of x undefined? If there are, then we call those values domain restrictions in the sense that those values are not a part of the domain. Those are not x values which can be used. If we think about the function on the previous slide, it was f of x equals 1 over x. The x value you can't use is 0 because it makes the denominator equal to 0. And with these rational functions, pretty much exclusively, your domain restrictions are going to be places where the denominator is equal to 0. It doesn't necessarily mean that x equals 0, but it means that the whole denominator is 0. So if I have a function like this is a rational expression because there's a expression with variables in the denominator. And the value that makes the denominator equal to 0 here is 1. So like the domain restriction here is x can't be 1. And just to review, we usually write these with interval notation. And so the interval notation for the domain of this function would be this. Negative infinity to 0, and then 0 to infinity. The parentheses mean that you don't count 0. If we were talking about the domain of this one, we would say the domain is everything less than 1, and everything bigger than 1, and again, not counting 1. So are these functions, these rational functions, are they continuous? No. Do they have domain restrictions? Almost always, yes. Another word we're going to use a lot is asymptote. The P is silent. It's not asymptote. And the last syllable is tote, like a tote bag, like totally awesome. Totes my goats. Not taupe, like isotope. It's asymptote. Asymptote. Say it with me. Asymptote. So an asymptote is defined mathematically in a certain way, but it is defined. We could talk about it in this context. An asymptote is a line that a graph approaches but never quite reaches. That's not exactly right. And there's many functions where it does reach it, but doesn't ever get there. The specifics are not vastly important. I mostly want you to be able to recognize them and write the equation of it. So if I drew a line right, like this function is like approaching this line, but it's never quite going to reach it. We usually write these dotted to indicate that they're not a part of the function. Like if you wanted to graph all the points that satisfied this equation, all the x's and y's that make this equation true, like, I don't know, like when x is 0, y is 1 over 8 plus 2. So the point 0, 1 over 8 plus 2, which is 17 over 8. This is on the function, and that's this point right here. But like none of the points on the asymptote are actually a part of the function. So we usually draw it with dotted lines. That's what I'm trying to say. And this one has 2 asymptotes. Maybe you can see. I'm going to draw one. I'm drawing both dotted. I'm going to draw one in red and one in green so we can distinguish between the two of them. And if I were asking you about these, there are 2 asymptotes to this graph. Well, this green one, we would call we call that a horizontal asymptote. A horizontal asymptote. And that's just an asymptote, which is a horizontal line. And we can name this line. It's a horizontal line. It goes to y equals 2. So this is the equation of this asymptote is y equals 2. The vertical asymptote, which is the red line, I'm going to write vertical asymptote. Is a vertical line, and it goes through x equals 8. And so that is the equation of that line is x equals 8. And let me be clear, the equations of asymptotes, this is the equation of a line. Equation of a line. And this is what I mean and why I'm emphasizing that. If I ask you what the horizontal asymptote of this function is and you say 2, that's wrong. The horizontal asymptote is the line y equals 2. It's not just 2. 2 is just a number. An asymptote is a line. So when you write the equations of asymptotes, make sure you're writing y equals or x equals before it as appropriate. And you can, maybe you have some trick for remembering it, but horizontal asymptotes are always going to be y equals a number, and vertical asymptotes are always going to be x equals a number. So that's how asymptotes work. That's what they look like, and this is what the equations of asymptotes look like. I will regularly abbreviate this as HA, and I will abbreviate this as VA, just so you know what I mean when I say those things. HA is a horizontal asymptote, VA is a vertical asymptote, it's just shorthand. We're going to do this a significant amount. We're going to find the domains of these functions. And like I said before up here, domains of these functions are almost exclusively where the denominator is equal to 0, because we can't have zeros in the denominator of fractions. So if I have a rational function here with x's and stuff in the bottom, I'd like to know what values of x make the bottom 0 so I can not include those. So you could look at this and maybe guess some of the asymptotes, but a better way to do it is the question is, what values of x make this thing equal to 0? X equals 0 doesn't work. When x is 0, the denominator of this fraction is -10. So the way that basically we're going to solve this little equation, we want to solve this equation, x squared minus 3x minus 10 equals 0. The values of x that make this equation true are the ones I am not going to include. They're the ones that make this function undefined. One way to do that is to factor it. We spent some time talking about how to solve quadratic equations in this course. This is one way. Factor this, does that work? Yeah, and so I get x equals -2 and x equals 5. So the bottom here is really x minus 5 and x plus 2. And so this tells me that x cannot be equal to -2 and +5. So the way I would write the domain is like this: -infinity to -2, -2 to 5, and 5 to infinity. And if I was asking you on a test, find the domain of this function, this would be what I'm looking for at the end. Would be that expression, that piece of interval notation right there. So just to recap how we find the domains of functions, the rational functions, is we figure out where the bottom of the function equals 0, and we do not use those values of x. This will come up a lot where the bottom is like an expression you have to factor to solve. Sometimes it's not. Sometimes, if you remember these ones, like this one, the bottom is 0 when x is 0. There's not a lot of work to do there. This one, the bottom is 0. If I was thinking about it the same way as the last one, I'd look at this and I'd be like, okay, so this thing, when x minus 1 equals 0, that means that x equals 1. Which means like I want to not include x. I don't want to use that one. So it's kind of the same thing. You set the bottom equal to 0 and see what values of x make that true. So here's a kind of an important point. It's about holes and versus asymptotes. So this is a rational expression. You can see there's x's in the bottom, but you can like immediately cancel out the x plus 3's. So here's the question. There's kind of two different expressions we're looking at here. If I look at this one, I say the values of x that make the bottom 0 are -2 and -3, which means the domain of this function should be this: -infinity to -3, -3 to -2, and -2 to infinity. So it's like all the values except these two. So that's a domain, fine. But what if I do this? If I write this, like I could cancel out the x plus 3's and I could be like, well, isn't this the same as x minus 5 over x plus 2? Is that the same as f of x? Well, numerically, all the values are the same. In a sense, like if you plug a 1 in here and you plug a 1 in here, you get the same number. So I guess in that sense, they are the same, but they're not quite the same. Because the only value of x that makes the bottom equal to 0 here is x equals -2. So x can't be -2, which means the domain of this function is -infinity to -2 and -2 to infinity. So like that's not the same. That's different. That's fundamentally different. This one has a whole value of x you can't even use, and this one doesn't have that value. You can see if I take this function and I plug in -3, this is undefined. But if I take this function, I'll call this f1 and f2 so that we know, because these aren't the same. If I plug a -3 into the bottom function, just to see what happens, I get -3 minus 5 over -3 plus 2, which is -8 over -1, which is 8. So like that's a fundamentally different thing. When I plug a -3 into this one, I get nothing. It's undefined. When I plug a -3 in this one, I get 8. So those are clearly different. So the answer to the question, does that change the domain? No. These functions, this one, F1 here and F2 here, these functions are numerically the same except for -3, but that's enough to make them not the same function. So it doesn't change the domain. You might simplify this, but the domain of f of x, F1 is still this. So just keep that in mind. Here's what that means. If I graphed the whole thing, the F1 that I called it up here, F1 of x, and this must be F2 of x. Like I get these two branches like I kind of expected from a rational function, but there's a hole when x is -3. So what that means is like, you can't plug -3 into here. So the way that that's reflected in the graph is that there's like a hole, like an open circle. We call that a hole. Technically, it's called a removable discontinuity. You don't have to know that this year. You will have to know it in pre-calculus. But for the purpose of this class, we're just going to call it a hole. And this function, when you cross off the x plus 3's, you like remove that restriction. X can be -3 in this one, and so there's no hole in this one. Might be interesting to note, we saw that when we plugged -3 in, we got 8, which means that in this function, when x is -3, y is 8, like that point is on this graph. And that's exactly where the hole is in this graph. Like it's this point got removed when you have the x plus 3 in there. So that's why they call it removable discontinuity. So this is important, and then I'm going to stop this video. When can you cancel something out of a fraction? This is super common, a super common mistake. You can do it when that particular something is multiplied by every term in the numerator and denominator of the fraction. That's always been a rule, no matter what grade level you're in, though it's very common for students to cancel things out that don't fit this criteria because it's easier and it looks like something you can do, even though it's something you can't do. And you've never seen a math teacher do it in your life, but it's a very common mistake. So I want to kind of address it now. Another way of saying this is when that something is a factor of the numerator and denominator. Nope. Numerator and denominator. That's what it means when I say multiply by every term. It means it's a factor. So that's when you can simplify. That's when you can cancel things, and otherwise you can't do it. When can you not do it? Any other time. Like this is the only time when that works, is when it's a factor of the top and the bottom. So I'll leave these. We can talk about this in class. This is something I'm going to want to say again when we get back to class. So we'll talk about these two when we get back there. I just want you guys to have heard me say it once, and then we're going to do some examples in class. So keep an eye out for the next video. It's coming up.